All right, so now we're gonna cover more just about time varying signals and waveforms. So we've covered this before a little bit, but we want to repeat it, right? So in general, you refer to electrical signals depending on their current. You have DC signals, direct current signals, where the signal only proceeds in a single direction, i.e. I have a positive voltage, I'm going from positive to negative. I can have variations in the level of this voltage, but the point is it never goes negative and the current never switches direction. The other term we use is AC, or alternating current. And these are signals that go positive and negative. The current changes direction. So when we say a waveform here, what we're talking about is some electrical signal that varies with time, right? You know, you can have waveforms in other mediums, waves in the water. Electromagnetic radiation is waves of light in the but the point is what we care about here are varying changes in voltage or current. So, and what we're talking about is a change in amplitude with respect to time. So we have here, for example, some voltage that's changing over the course of a second, right? This entire thing is what we would call a waveform. So for those of you who have not dealt with waves before, there are a few characteristics of a wave that we're concerned about. So what we mean by a wave is some sort of periodic signal that repeats itself in a pattern over time. So how often that signal repeats itself within a given amount of time is called the frequency. It's measured in hertz. And 1 hertz just means it's run through one complete cycle in 1 second. 2 hertz, 2 complete cycles, et cetera, right? The time that it takes for that complete cycle to occur is called the period. So I start here, I go all the way up and then down and then back to my starting point. That's 1 cycle. So this time here would be the period. And it's important, like there's a fairly simple relationship between frequency and period. They're inverses of each other. Period or frequency is 1 over the period and period is 1 over the frequency. We refer to the, this peak value, this maximum value as the amplitude. That'll be measured in volts or amps, depending on what sort of signal we're talking about. We're concerned about the distance from 0. So when we say the amplitude, we're going to always call that a positive, right? This is a negative value, but we would say, that's the same amplitude as that, especially for something that repeats like that, where there's not really a reason to choose, oh, this is positive and this is negative, right? You could easily invert the whole thing. So usually a frequency and an amplitude are the 2 most basic things that tell you, describe the wave, right? Once I know that, I can draw a sketch like that. I know the 2 most important things about the wave. So I think we've also mentioned this before, but we've got two types of signals in another way. We've got analog and digital signals. When we're talking about analog signals, we're talking about some continuously varying signal over time. They can basically take any possible value between their minimum and max. But you're going to be more worried about noise and distortion and interference in an analog signal. Because you're often dealing with a continuous voltage output, analog signals are very common as an output from a sensor. And again, the corresponding type is a digital signal, where you have discrete possible values that vary over time. Typically, if we're talking about a signal, there's often just two values, a high level and a low level, right? Logic high, logic low, 0 and 1. And we usually use this as a way of communicating a particular signal, encoding it in the pulses here. And what's nice about these is because there's only the two possible values, you don't really have to worry too much about interference and distortion, right? If I bump one of these slightly, well, I know it's still well below the high value. And again, digital signals are how we're going to do any sort of processing with the CPU, any sort of logical operations, and a whole lot of integrated circuits are going to use digital signals to communicate. A particular type of digital signal is something called a clock, or a clock signal. And you usually use that if you want to synchronize different devices. You know, if we want to synchronize operations across two different integrating circuits. The frequency of the clock signal is how quickly operations will be performed. So for example, your devices will perform one operation on every single complete clock cycle. So usually you trigger on one of the edges of the clock pulse. We can either trigger on this edge here. That's called a rising edge because it's the edge of the pulse and it's going from low to high, it's rising. Or we will trigger on the falling edge, again, going from high to low, it's falling. So if we have signals that are accompanied by a clock, that's what we call a synchronous signal. What we care about is what the value of this data is at that trigger part of the clock. So the clock is what's dictating units of time. You could think of each one of these pulses as a tick of a clock. And what we're going to do is we're going to look at the values of this command line at the appropriate edge of the clock signal. This change tells us to look at, okay, what is the value of the data signal right now? So for example, you can see this is actually a falling edge. So first falling edge, I look at the clock signal. It's low, so I get a 0. Next falling edge right here, the clock or the data is high, so I get a 1. And I can do that for all of these. So on this 1, 2, 3, 4, 5, 6 clock pulses, I got 6 digital values out of the data, and this is what they are, right? But we need some sort of equipment to actually look at these signals, and a simple multimeter is not going to do it, right? Multimeters are slow, and they're usually going to report some sort of averaged value of the signal. It's just they're not really designed for rapidly changing signals. So if I have something that's pulsing from -5 to 5 and I put a DC multimeter on it in particular, I'll probably get 0. So often that average value can be very different from the amplitude, and in particular, if it's just a DC voltage or current, you're not going to know anything about the frequency. However, a lot of multimeters will have an AC setting where it will give you an amplitude and a frequency. How those behave on something that is not like a clean sine wave, they may not work that great. So in general, what you want to use is an oscilloscope to look at if you have something that's a rapidly changing signal, you're going to use an oscilloscope like the one pictured here. So what an oscilloscope is going to output is it's going to output a changing signal with time, usually voltage. So the screen, you'll get a little 2D plot with a y-axis that is usually voltage and an x-axis that is time. So what's really nice about this is you get these nice time plots of the signal in real time. So you can use it to identify, timing issues. So for example, if you've got one of those clock signals and a data signal, you can actually look and see, oh, my data isn't properly synced up with my clock for some reason. I can look for, hey, is this brief pulse getting all the way through my circuitry? Is the signal getting all the way through? So basically any sort of situation where you have a time varying signal, you're going to want to use an oscilloscope if you need to do any observation of that. Instead of the simple probes that you have with the multimeter, you've got these oscilloscope probes. Usually, often these probes will have an attenuation factor. They'll be like 10x, 100x, or maybe 1x, right? And that'll be a setting on the actual probe itself. So it may be written on the base here, or it may have a little selector switch where you can have multiple types. And mainly this is used so you can have higher voltage signals going to the oscilloscope. The oscilloscope is, not really meant to take very large signals. So what you need to watch out for is, in particular, if you have like a digital scale, you want to match the setting of the attenuation so that your readout is correct. So when it's at 5 volts, when you're reading 5 volts on the oscilloscope, well, is it actually 50 volts because you have a 10x attenuation probe hooked up. So you have basically 3 parts. You have the connector here that connects it to the scope. That's called a BNC. That's just what that type of connector is called. You've got the actual probe right here. And then you've got this little grounding clip right here. So this is going to be what gives you your 0, right? So to measure a signal, you have to have both of these connected, right? If I don't have the grounding clip connected, I don't know what my voltage is in reference to. This is like your negative probe of your multimeter. This is your positive, right? If I just touch one of the probes of the multimeter to my circuit, that doesn't tell me anything. I have to touch both ends. When you look at the display, if you have a modern digital oscilloscope, it's going to look something like this. You may have an old purely cathode ray oscilloscope, which are going to be a little bit trickier to use. So you can see here there is a grid. So there's horizontal and vertical grid marks. It's a little bit hard to see on the screen here, but you can see it's basically major and minor marks, right? I've got my actual signals here. These are called signal traces. Over on the left side of this particular, there's a little dash mark or arrow that shows the 0 for that particular channel, because I can actually adjust the scope so that these signals move up and down, because I may not want them right on top of each other so that I can actually see them independent of each other. So you can see there's a little arrow here and a little arrow there, and that's where the actual zeros are for those two different channels. There's a vertical scale here, or in the center often, and then there's a horizontal scale, and then you'll usually have, you know, your menu which displays down here. And also you can see that here is my scale for my two channels. So channel 1, 50 millivolt. So that means each big square is 50 millivolts. Channel 2, it's a 100 millivolt scale. So even though these look like the amplitude is the same, channel 2 is actually twice as big of a signal because the scale is twice as big, and they match here. And then I also have the horizontal scale. So each horizontal segment in this case is 500 milliseconds. So, you know, obviously you need to be able to change those scales. You need to, you know, move them up and down. So there's going to be a whole bunch of controls. You know, a lot of modern scopes are going to have automated displays, so you can sort of have it attempt to automatically size to your waveform, and they'll be able to do some measurements on the waveform. So they'll be able to output a peak-to-peak voltage, average voltage, a frequency, right? These are all values that can be calculated by a modern digital scope pretty easily. Without, you know, knowing what model of scope you have, it's really hard to tell you how to do that. So basically, you want to look at the manual for the particular scope that you have access to. You want to familiarize yourself with all the different menu options. The actual shifting of the waveforms is somewhat standardized and usually very similar across multiple scopes. So there's one thing to note is that there's a common time scale across for all of the signals, right? So I can independently adjust the vertical scale, but there's only usually going to be a single control for the actual horizontal scale. So this is should say the horizontal axis is going to be measured in units of time, seconds, milliseconds, microseconds. Nanoseconds are fairly common resolutions on scopes to see. You know, it'll be that scale will be displayed somewhere on the screen. And then if you look at the actual knobs, you'll have a horizontal adjustment which shifts the signal left and right, and then a scale adjustment which will make the scale either shorter or longer, right? It'll increase or decrease your time resolution. For the vertical adjustment, so you may have a few different ways. So you may have a different set of knobs for each channel. So you can see on this scope, there's a channel 1 plug and a channel 2 plug, and they each have their own independent adjustment knobs. In this model on the left, this 1, 2, 3, and 4, those are our 4 actual input channels. So to adjust one particular channel, I need to hit the button and then I adjust the appropriate settings. If I want to change a different scale or a different channel, I need to hit the button first and then make the adjustments. So yep, the vertical axis is usually going to be volts. And for these, you can independently adjust the position and scale of each one. In particular, it's easy to see, you know, if I have 2 signals that I'm trying to look at the same time, I may want to shift them off of each other so they're not right on top of each other so I can see each complete signal. Or I may want to make them match so that their zeros line up with each other so I can see how they compare with each other. Another important setting, and that usually has its own knob to the right of the other ones, is the trigger level setting. So you can set it so basically that once I cross this trigger level, either going up or going down, that's usually a option, you can pick one or the other. That's when it will record. So, and it'll record, you know, some fixed amount of time around that trigger. And what this will look like is you'll usually have a little arrow on the right side of the display. And as you adjust it up or down using this knob, you'll get a horizontal line that'll appear. But what this lets you do is if I have a, you know, something that's a rapid signal that, you know, maybe only happens very rarely, it's only a couple of microseconds or milliseconds long, and then I have a couple of seconds idle. If I was just to have the display continuously recording, I would basically 90% of the time be looking at a flat line and I wouldn't see it. So what this will do is it'll let me capture that signal, trigger on the event that I care about, and display that. So usually in conjunction with that, you're going to use what's called like the run stop button. So I can hit, for example, this single sequence. So when the trigger happens, I'll get that particular trigger event, and then the display will freeze. I can then use the run button to resume recording. Or I can often just hit the run stop button to pause the display in the middle, and it'll just show what is currently displayed. So again, this is all useful for when you're looking for something that happens very quickly, right? Because I can get that horizontal scale down to nanoseconds. So I don't want to continuously be rewriting it, because I'm at the most, you know, I may have only 10 nanoseconds of span there. So to be able to actually see what's happening, I have to look at it in 10-second chunks, and I want to look at the chunk that has the thing that I care about. So I'll set the trigger so that it'll go off on a particular condition that I want to capture. So that's sort of it for the time varying and, you know, tutorial for using an oscilloscope.